Okay, so I suppose I'll start. So I welcome you to this problem solving and live interaction session for the subject engineering mechanics. Today we will be looking at problems from the last week, week 12, which has to do with 3D kinematics. So let us delve into the problems. Okay, so the first question here asks us the following. Select the correct statement. Finite rotations are vectors, but infinitesimal rotations are not. Both finite and infinitesimal rotations are vectors. Infinitesimal rotations are vectors, but finite rotations are not. Finite rotations and infinitesimal rotations neither are vectors. So what do we know about vectors? Vectors have to basically follow one law. That is, the vector should be commutative. What does that mean? Let us say that I have my xy coordinate system like this. X, Y, and then I have z coordinate pointing out of the plane of the sheet. So if I were to operate it by some vector, let us say the rotation I give theta vector I give is let us say delta I cap plus beta j cap. Let us say that the rotation I introduce is delta I cap plus beta j cap, and I introduce this rotation in parts. So if it happens that first I rotate it about I might not be able to show that rotation now. What we can do is, as done in the book, as done in the lecture, we can take some object, let us say, and I rotate it about the plane of the screen by 90 degrees. Let me show it this way. Let me take this object, the calculator, and I rotate it about the plane of the screen first by 90 degrees, and then I rotate it this way about this axis. So this is my final position. Whereas if I were to rotate it first like that and then rotate it by 90 degrees as I did, I'm able to see that this plus this is not this plus this. So both the orientations are different. We are clearly able to see, which means the order matters. The order in which we apply these transformations matter, in which case these cannot be commuting. That is why finite rotations cannot be treated as vectors. And a detailed proof of this from mathematical perspective is already discussed in the lecture. So, how we can identify, if we were to limit these rotations to infinitesimal quantities, then it wouldn't matter in which way we apply these, given that the quantities are small, which is why infinitesimal rotations are vectors, which is why if infinitesimal rotations are vectors, then what we do is we express them as vector quantities and then take its time derivative and double derivative and so on. So we will get omega alpha and so on. So that is what we have been dealing with essentially. But the broader strokes in the broader picture being that infinitesimal rotations are vectors, but finite rotations don't commute. The order matters. That is why they are not vectors. So I hope that that is clear. So far in 2D kinematics, we have looked at a lot of examples, how to analyze absolute motion, how to analyze motion using relative analysis. Basically, we take a body, a rigid body, we take one point whose velocity we can gauge, uh, possibly some constraint point or the mass point. And then we look at another point and invoke our circular motion, circular motion equations by virtue of the r being constant because of the rigid body constraint. And then now this axis we attach to that point, maybe the mass point or the constraint point, that could be that could be non-rotating translating axis, or it could be rotating as well. So if it rotates, it has to bring about additional quantities like vrel and 2 omega cross vrel, arel, all these we saw how these come. But so far we have discussed examples where our omega where our omega and alpha. Basically, these only alpha was a result of the magnitude. Say I am taking that alpha is omega dot k cap. Given that omega is omega k cap, then alpha represented omega dot k cap. What does this imply? This implies that so far we have been looking at examples where the angular acceleration is brought about by the magnitudinal change of the angular velocity. Now we are relaxing this constraint. Now we know that our omega can be some delta I plus beta j in general plus some other alpha k, not alpha, let me take some other Greek letter, gamma k cap. Now what will happen is alpha, when we see, we will have to systematically take its time derivatives. What does that mean? Omega dot I plus beta dot j plus gamma dot k. This is what we have been dealing with so far. Now our axis also will rotate. So this will have plus delta I dot plus beta j cap dot plus gamma k cap dot. Now there would be cases where some might not change, this will go to 0, but I'm expressing it in the most generic fashion. Once we do it systematically, we will understand how to go about doing this. So let us say that there is a vector here, and after some time, let us say that it rotates and comes here. Now what is the vector connecting this? Ideally I should, let me make the magnitude same. Let us say that this is, its magnitude is same, and then I have a vector like that. This will be at 90 degree. It's not coming correctly, 1 minute. Now this has rotated like this. It's the same vector. Only difference is this is after some time t. So what will be the connecting vector? This will be my connecting vector. Let us say this quantity is r. This vector is r. And let us say that this goes through some delta theta. And this is r1. So what is this quantity? Can we see that this is nothing but r delta theta, given very small rotations, infinitesimal rotations. In which case I can see that r1 vector is r vector plus r delta theta. Now this delta theta is also a vector. It is a angular displacement we are giving with its axis out of the plane of the paper. In which case the difference, if I normalize this, what will that be? It is delta theta, the vector. I am dropping the vector because it is out of the plane of the paper. Now in the limit delta theta tending to 0, if I take its time derivative, what does this come out to be? Delta theta by delta t in the limit for a time, not this thing, for delta t, for a very small time instant, this will be nothing but our omega. What does this imply? The implication of this is that it is already discussed in rotating frame of reference, but nonetheless I'm repeating it. What this implies is, let us say that there is a vector r. If the basis with which this r vector is represented rotates with some omega, then r dot, the whole vector, first r will be represented by r some n cap. This is how we generally represent some vector, r n cap. R is the magnitude, n cap is the direction cosine. So r dot will be r dot n cap plus r n cap dot, which will be r dot n cap plus r. Now this n cap dot is represented by omega cross n cap. This is the key understanding that we need to form here, that when a basis rotates by some omega, its time derivative, this is how we will represent. And this, when we systematically differentiate, this will keep coming in. So we will look at some examples so that it becomes clear. Okay. So let us see this. An antique pedestal fan is having angular motion with constant angular speeds. So all the magnitudes are constant is what is given as shown. So what do we see here? We basically see there is a stand like that, over which we have this mounted, the circular piece is mounted over that, and it is having angular motion. So what does this first point imply? That this is having angular motion first of all like that, which is omega 1. And then about this point, this fan is having a rotation like that, which is omega 2. We have been given the axis. So we have been given this is x, we have been given this is y. So we can naturally see that x cross y is out of the plane of the paper. Okay. Now what is asked is answer the sub questions based on the given data. Select the unit vectors x, y, I, j, k, whatever, along which the instantaneous angular velocity vector of the fan blades has no components. So if we write the angular velocity vector, instantaneous angular velocity vector of the fan blades, we can see where it will have no components. Now let us say that I first connect myself to the this frame, this pedestal. What will I be seeing? First of all, I rotate with omega 1, which is along what? Which is along k cap. I hope you are able to see that that is along k cap upwards. So this is omega 1 k cap. Plus then I see that this fan is rotating with omega 2 about minus k cap. Sorry, this will be j. I am so sorry. So the omega of the blades or the hub, whatever you want to call it, it is omega 1 j. It is this omega which has its axis along plus y, which is positive j cap, and then I see that it will be plus omega 2 along minus k cap. So omega of the blade is nothing but omega 1 j minus omega 2 k cap. So this is, we have got this. So this is no longer along one direction, but that axis is also rotating. So whatever is k now, that is pointing into the plane of the paper. We have k cap pointing out of the plane of the paper right now. At the next instant, it will be pointing like this. Next instant, it will be pointing like this. So that is also having a rotation. That is what makes it a 3D kinematics problem. So we can clearly see from here that it has j and k component, doesn't have I component. So the answer is the instantaneous angular velocity vector doesn't have I component. Now let us see the next question. Select the unit vectors along which the instantaneous angular velocity acceleration vector, the instantaneous angular acceleration of the vector has non-zero components. So now we have this. Let me take it here. We know that angular acceleration of the blade is nothing but its time derivative, which is nothing but omega 1 j minus omega 2 k. We have to take the time rate of change of this entire quantity. So what we can do, we can systematically differentiate this. So it will be omega 1 dot j cap plus omega 1 j cap dot minus omega 2 dot k cap minus omega 2 k cap dot. Now once we have written this, then we can see from the question which are the quantities that exist and which are those that don't exist. Now we have been given in the question that all are dealing with constant angular speeds, which means no magnitude change. None of the magnitudes change. What does that imply? That this quantity is 0, this quantity is 0 because magnitudes no change in speed. Okay. Now next we need to see which is the vector that changes with time. As we saw, if this is k cap, next this is k cap is changing its orientation constantly because of the virtue of this omega 1. Whereas j cap still remains the same at any, even after some time when the blade is like that with its k pointing there, j still remains the same. So j cap is not having any time, having any change with time. So that is another insight we need to take from here. So this happens to be the only rotation that is bringing about a change. So what does this imply? Or the blades is nothing but minus omega 2 k cap dot. Now we saw that k cap, what is the rate of change with which k cap is changing? It is omega 1. So we saw here that once n cap is changing in a system where which is rotating with omega, its time rate of change will be that omega crossed with that vector. What does this imply? So this gives us minus omega 2 into, this is omega 1 vector crossed with k cap, as we saw. Now we know what omega 1 is. What is omega 1 vector? Vector is nothing but omega 1 along plus j. This we know. This is what we have written here. So from here it follows that this will be minus omega 2 into omega 1j cross k. Now we know how to do cross products. I, j, k. So j cross k will be positive I. J cross k is positive I, but we have a minus here, so we will just account for that. So this will be minus omega 1 omega 2 I. I hope this is clear. So if there are any questions, please go ahead and ask. We can see it from here also. So we have positive k cap and then positive j cap, and then we have the angular velocity pointing inwards. K cap, it's this thing is pointing inwards. So its actual direction will be, by taking the right hand rule, it will be pointing in the negative x direction, which is what this is. So okay, we don't need a new page for this. I'll just write it here. So this is what it is. Yeah, so what did the question ask? The question asks, select the unit vectors along which the instantaneous angular velocity vector has non-zero components. So we saw it has only I cap. So this also happens to be I cap, as same as the previous but for different reasons. So I hope that that is clear. So with this, let us move on to the actual analysis of systems where it has motion like this. Okay. So it says a wheel of radius 0.35, a wheel of radius 0.35. So we have a wheel which has a radius of 0.35 meters, steadily rotates with a constant speed beta is equal to 0.15 about q. So we have a point q here, about which, so this is the direction of beta that is given. We've been given that beta rotates like this about q. So the rotation is like that. Okay. About q, which in turn is connected to a shaft PQ. So we have the shaft PQ and rotating about the vertical with a constant speed of delta. So there is a connection like this, and this shaft is rotating. So the next instance shaft will be like that, then it will be like that. It will go. It is rotating like this. Okay. At some instant, the point R on the rim. So this is the point R on the rim of the wheel makes an angle theta as 135 degrees with the vertical as depicted. So we have the vertical. So this is at 135 degree. Why this theta is given? Basically to find out the position vector of that point. Considering the positive coordinate directions as shown. So does this follow? X is here, Y is here, X cross Y is Z. So this follows the right-handed coordinate system. Very well. So answer the following questions at the instant depicted is what is asked. Let omega represents the instantaneous angular velocity of the wheel. What are its XYZ components? Let VR represents the absolute instantaneous velocity of point R. So what are its XYZ components? What is the magnitude of the instantaneous acceleration vector of the wheel? What is the magnitude of the absolute instantaneous acceleration of the of point R? So in essence, what have we been asked is first we find out the angular velocity and angular acceleration of this wheel due to the combined set of all these motions up. And then about this point R, what is the velocity of R? What is the acceleration of R is what is asked. Now, if we were to ignore the shaft PQ initially, what would we write as the angular velocity of wheel? We know that it is rotating like that about point Q, which is along minus y. So can we see that if this is the rotation, then if I curl my fingers like this, my thumb points in this direction, which is nothing but minus j cap, and it rotates with beta. So it is nothing but beta j cap. This is yeah, there is some lag. 1 minute. Minus beta j cap. Okay. And then this is also having, due to this change, it is also having a rotation about the vertical, which is nothing but plus delta k cap. So this is the total angular velocity vector of the wheel. So this accounts for its change about q, and then the axis itself is changing. So this has to be brought in to account for that. In such a case, can we substitute the values? What this is? Beta is given to be 0.15 and delta is given to be 5. So omega of the wheel is nothing but minus 0.15 j plus 5 k cap. So this much we have found. So x component is 0, y is minus 0.15 and this is 5.0. Okay. So if we have the angular velocity vector, can we calculate the angular acceleration also? If we have the instantaneous angular velocity, so alpha of the wheel, we know it is omega wheel dot. So let me represent it in this form instead of this, so that because when we write numbers, we automatically consider them as constants. It is better to go by symbol first, differentiate, then from the question gauge whether excuse me, whether the quantities are 0 or not. So this will be minus beta j plus delta k entire dot. What does this give us? So this will be minus beta dot j cap minus b cap j dot. plus delta dot k plus delta k dot. Okay. So in the question we have been given that it is constant speed beta is constant and delta is also given to be constant. So these two terms, these two words help us identify that there is no magnitudinal change, in which case this is 0, this is 0. So now let us see which is the axis that is changing here. So we have x pointing here. In the next instant, uh, this is x, y and x, y and z. Now we can change the, we can see that the component y at this instant it is like that. At the next instant when the wheel is over here, it will be like that. So y is changing as we rotate, whereas this still remains the same. The vertical is not changing. So k cap dot is essentially 0. This quantity is 0, whereas this is changing by virtue of that shaft rotating about the vertical. So this goes to 0. So in which case alpha of the wheel is nothing but minus beta j cap dot. Now we have the recipe how to find this out. J cap dot is omega. We know that n cap dot is omega cross n cap. This we know. I'll just put it here just in case we need it. So what is omega? Omega, due to which j cap is changing, it is delta. Because by virtue of delta, first of all the disk is over here and our axis is like this. After some time the disk will be over here, the axis will be like that. After even after some other time, j will be like this. So it is constantly changing. So this will be delta. What is delta? Delta is k cap, delta vector crossed, k cap crossed with j. Now again I, j, k. So we can see k cross j, we are going in this direction. K cross j is minus I. From the figure also we can see k cross j. This is k crossed with j will make a thumb point in the negative I direction. So this will be minus beta delta minus I cap, which makes it alpha of the wheel as beta delta I. Very well. So if we were to substitute the values, what will this come out to be? So we have beta as 0.15 and we have delta as 5. So 5 into 0.15 I cap. So what is that amount? Quantity is 0.75. So alpha of the wheel is 0.75 I cap. So for the wheel, we have been able to gauge what is omega, what is alpha. Next, we will focus on this point R, for which this is asked. So let us go about doing that. In fact, let me take a, yeah. Okay, so now we know rotating frame of analysis, rotating frame of reference analysis we know. So let us say that we attach one rotating frame here at point Q, where this is X, this is its Y, and this is its J, K, Z, sorry. I'm sorry about that. Yeah. So with this coordinate, if I were to attach this rotating frame of reference to point Q and then observe, that is essentially what I'm doing here by attaching this is I'm rotating with this shaft. So once I rotate with the shaft, what is it that I observe? I observe this disk to be rotating with beta. So if I were to place myself here, let us say what is velocity of Q? So velocity of Q becomes, let us say, by relative motion analysis, we will have velocity of T plus delta K cross R of Q with respect to P. This we know if we attach a frame here and then this is my velocity vector, so I will be able to gauge its velocity. I know that this is not going anywhere. Velocity of P is 0. So velocity of Q comes out to be delta K cap cross, what is Q with respect to P? It is 1.5 I. 1.5 I. So K cross I. K cross I is J. So velocity of Q is nothing but, what was delta's value? Delta was 5. So this is 5 into 1.5, which is 7.5. K cross I is J. So we have velocity of the coordinate. We have velocity of the coordinate. Similarly, we can calculate the acceleration of the coordinate. So we know that this will be what? Acceleration of T plus delta K cross delta K cross R of Q with respect to P, which is centripetal, which will point towards P, plus what is delta dot K cross R of Q with respect to P. Now we know that there is this speed is constant. This is not changing. So there will be no tangential acceleration to the coordinate. There will only be a centripetal acceleration by virtue of that rotating in a circle of radius 1.5 meters. So this clearly goes to 0. This quantity is not going anywhere because this is sitting at the point at this point. So what is acceleration of that Q? It is centripetal acceleration. Now if I do the cross product, I'll get it pointing in this direction. I know that it will come in this direction because it is centripetal and it has to point towards P. What is this direction? It is minus X. So it will be minus something I cap. So what is that? Delta squared into 1.5. So 5 into 5 into 1.5. So it is 37.5. So we have got velocity and acceleration of the coordinate. Very well. Now we have attached our rotating frame of reference to point Q and we are looking at point R. So first, let us, for convenience, let us clearly write what R vector is with respect to this Q. That is, what is this vector is what I am saying. Let us write that. So we can clearly see that it is in the xz plane. This vector is in the xz plane and it will be nothing but having components. Its length is 0.35. So 0.35 cos 135 will give me the k component. 0.35 sine theta will give me the x component. So r of r with respect to q is nothing but 0.35 into cos theta cos theta k plus sin theta I. This we have to gauge because in the xz plane. And what is theta? Theta is given to be 135 degrees in the question. It is given to be 135 degrees. So this means this will be 0.35 cos 135 k cap plus 0.35 sin 135 I. So if I write I first and then k later, this won't be theta, this will be r of r with respect to q. It is nothing but 0.35 sine 135. So this comes out to 0.247 I, and then the other component would have to be negative because it is pointing. Yeah. So this is minus 0.247 k. So we have got this. Very well. So now we know that when we have, just a moment. Yeah. So now we know when we have the coordinate attached to this point and we are looking at this point. So what can we calculate? If we have velocity of r with respect to q in terms of RFR, what does that quantity represents? That quantity represents VREL. Similarly, from the RFR, if I look at this point and the acceleration that I calculate, that will be AREL. So when I sit at this point and look here, the velocity which I will see is VREL, which will be beta across this. It will be pointing like that. And when I sit here and look at point R, what is the acceleration that I will measure? It will only be centripetal, pointing towards point Q by virtue of this being a disk. Other than that, beta is constant. Beta doesn't have any time magnitudinal change, in which case ARL will be pointing in this direction. So let us calculate that. Ultimately, what we are trying to do, the broad stroke is velocity of r we want to calculate. So velocity of r will be velocity of q. We have attached the RFR at q. So from the RFR, what do we know? How do we calculate velocities? So it will be omega of the RFR cross r of r with respect to q plus VREL. This we know. Similarly, acceleration of r, we know that acceleration of q, absolute acceleration of the coordinate plus omega RFR cross omega RFR cross this plus alpha RFR cross this plus 2 omega RFR cross VREL plus AREL. This we have done umpteen number of times. That once you have a rotating coordinate, how you will calculate the absolute acceleration and absolute velocity. First, whatever is the rotating angular velocity of that coordinate and the position vector that you are looking at, and then the relative velocity, all these things will get added up. Similarly, omega cross r plus alpha of the coordinate into that position vector plus what is the corrective measure that we need to take by virtue of us rotating. It will be, since we are observing VREL, we will have to change for this, and then acceleration relative. So out of this quantities, what is it that we know as of now? We have just started our analysis and we have found out this. VQ and AQ we have found out. So this quantity we know, this we know. How? We have calculated it here. Where did that go? Yeah. We know what VQ is. We know what AQ is. These two we have calculated. Do we know omega of the RFR? We have attached it to attaching this. Yeah. So we have attached the what is this rotating with? We know it is rotating it with delta. This coordinate system, after some time, it will go here and it would have rotated in some way by virtue of this delta. So we know what omega RFR is. So this is nothing but delta. Alpha RFR will be delta dot, which is 0. In this case, this will be equal to 0. We can write these quantities easily. Now what is left for us to find out is VREL and AREL. Once we know those values, we just need to plug it in here and do the algebra and we will get the final quantities. So let us go about doing that. VREL. So now that we know this R, we know this. We know the wheel rotates with minus beta j angular velocity about q. So sitting at q, we can see that V relative is nothing but minus 0.15 crossed with this R of R with respect to our Q, because we are sitting at Q and we are looking at R. We can see that velocity of point R will be this. So which is nothing but minus 0.15 J crossed with this quantity. This quantity as a whole. So what will this come out to be? I, J, K. So J cross I is minus K. So this will be minus 0.15 into 0.247, and then this will be J cross K. So it will be plus J cross K. So this will be I. So VREL will be 0.15 into 0.247. And then this will be plus 0.037 J cross I is K. I didn't write that K here, so that will be coming here. Does this make sense? Algebra is fine. Does this make sense to us? When we sit here and look at it rotate like this, by virtue of this rotation, by virtue of this beta rotation, this point will have a velocity like that. That velocity, if we resolve into x and z components, we can see that x and z component both has to be positive and equal by virtue of the angle being 45 or 135. So if I were to resolve this vector, this will be my z component, this will be my x component with both being equal. Do I get that as my answer? Yes, I am getting both these quantities and both are equal. So that makes sense. Positive x and positive z, positive z coordinate. So VREL I know now. So let me calculate AREL also. I'll just take this again. Sitting at the wheel rotates with this angular speed constant, and this is constant by the way. This quantity is constant. This quantity about q. Sitting at q, we can observe that the velocity, the acceleration of r. This is actually beta. Okay, beta j. So AREL will be, what would we write here? Centripetal plus tangential. We know this quantity is 0 because this is rotating with a constant speed. That wheel is rotating with a constant speed about the shaft. So this is 0. So what does this come out to be? AREL is minus 0.15 k j, sorry, crossed with this quantity. So what can I write about this? Crossed with this quantity we just now calculated, omega cross r, that we just did, and we found out this is the velocity. Beta cross this is what we did, and we found the result was this. So I will take this result itself, copy, and I'll put it here. Delete this. So this is what it is. That is what it represents. Okay, so again I, j, k. So till now we saw that when we were doing cross products, it was very straightforward because mostly all our angular velocities were about k cap and angular accelerations were about k cap. Now we are seeing this 3D kinematics in play. So when it is j, then j crossed with I. So that is why we need to familiarize ourselves by writing this and then doing the cross product so that it becomes easier and without any error. So this will be j cross I. So this has to be minus k j cross I. J cross I will give me minus k. That minus and this minus cancels out. So I get this term k, fine. And then next term will be j cross k. So this is in this direction. So this will give me positive I. But this minus is there. So I have minus 0.15 into 0.037 I. So again, AREL will be 0.0056 I plus 0.0056 K. This is my AREL. Now let us analyze it again. Does this make sense? It is having a negative I component and positive j component. Let us go back to the figure and analyze this. We are sitting here. We are looking at this point. 1 minute. There is a lag. Yeah, so we are sitting here. We are looking at this point, and then beta doesn't have any. This beta doesn't have any magnitudinal change. In which case, my centripetal acceleration will be pointing in that direction. If I resolve this into two components, one I'll get minus x, another I'll get plus z. So minus I cap plus k cap is what I should get. Am I getting that? I'm getting minus I cap plus k cap. So this makes sense. So it adds up. I'm sorry, there is some lag here because of some net issue, I think. Okay, I think it's manageable. Fine. So this makes sense. So we have got ARL, we have got VREL. So we have got all the quantities that we need for our computations now. So let me copy this. Now we are able to see one thing apart from all this VREL, ARL, cross products, all that jugglery that we are doing, all the algebra that we are doing. One thing we are clearly able to see is when there is three-dimensional rotation, meaning there is rotation in more than one coordinate, it immediately scales up a notch. All our cross products become a little more involved, and our analysis needs more intuition than it did in planar analysis. But essentially what we are seeing is still the same concepts we are applying. The only difference here in this equation earlier was that everything was in 2 dimensions. Now the vectors are in 3 dimensions. That is all the difference is. But essentially the derivations that we have done for analyzing vectors in rotating frames of reference, it still holds. Only that our computations become a little more involved. That is the only aspect here. And if we practice some problems for taking cross products properly, systematically, then I don't think this is anything. This is no different. 3D kinematics is no different from 2D kinematics in terms of computations. Okay, so let us put everything substituting all quantities that we have calculated. So we get VR. So first we need to substitute for VQ. Where did we find VQ? We found it here. It is 7.5 J. So we have this as 7.5 J cap. Then we know omega RFR is delta K. Alpha RFR is 0 because delta is not having any angular velocity. Time rate of change, sorry. So what is this? This is delta K crossed with R T with respect to Q, which we saw was this. This comes here plus VREL. VREL we have got here. Plus VREL. Similarly, acceleration of R will be, first let me get the parent equation, this one. By virtue of this being 0, I'll remove this quantity. This is not there. Okay, so what is AQ? Acceleration of q we had calculated somewhere. It is minus 37.5 I. So it is minus 37.5 I plus delta k cross this quantity plus alpha cross r is 0 plus 2 delta k cross what is vrel is this. This is vrel plus arel we have calculated. So we see all that we did in piecemeal. Now everything is being put together in order to find out the quantities ultimately. This is my arel. So I don't want to expand this right now. When I'll post the solution, I'll expand it. But this is how we are doing it essentially. So when the things were simple in 2 dimensions, it was straightforward, the cross products. Now just that complexity has come in. Other than that, there is no difference in the analysis. So when I post this, I'll solve this completely with the answers. In the meantime, if there are any questions, I'm happy to take them because I've been doing omega cross R for quite a while now. I understand that it could be a little dry if we just go on doing vector algebra. So other than that, if there are any questions, I'm happy to take them. Otherwise, I'll move on to the next question, which is a variant of this. We'll just see what that variant is. So in the meantime, if you have any questions, please feel free to ask. Okay. So let us look at this question. Yeah. So a tower crane operator observes the concrete block. This is the concrete block being lifted at a constant rate of 1.2 meters relative to the crane. When with the boom PQR, this is PQR. So this is the arm of that crane is constantly rotating at 1.5 radians per second as shown. So this is rotating like this. So can we identify what this direction is? We can see that it's when we curl our fingers, it is pointing in the minus z direction. So this is minus 1.5 k cap. Omega 1 is minus 1.5 k cap. So let us write that down. Omega 1 vector is minus 1.5 k cap. Let me not. Okay. It is also known that the crane rotates at 4 radians per second about the vertical at the instant considered. So this rotation is also given. Basically, we have the platform. How the construction is, we have the platform over which we have a tower. What happened? Over which we have the tower. Now this hub, it rotates about this tower with this angular speed, 4 radians per second. At the same time, that tower is being lifted with this angular velocity. And by virtue of that connection and this cable that is there, this is relative to the boom that concrete block is being raised at 1.2 meters per second. That's what the question says. Okay. So we can see that omega 2 is nothing but, if we curl our fingers again in this direction, we will see that our thumb points downwards. So this is minus j cap. So this is minus 4j. J. Omega 1, omega 2 we have written. Fine. Consider the positive coordinate directions as shown. So we have x, y. X cross y is z. It follows. Fine. Answer the questions is what is given. Let us analyze what is different from the previous question. Let us say that we connect our rotating frame of reference. Let this be the tip. This is the tip. Okay, let us consider this x, y, and I have this as z. So this is my RFR. In the previous case, what I saw was when I sit here, there was a disk, there was a point r, whose that disk's angular velocity was given, and I was calculating v relative by circular motion equations, omega cross r, accelerations by circular motion equations, omega squared r, centripetal, and alpha was 0, so there was no tangential. In this case, when I sit at the RFR, I am told that I am already able to see what VREL is. VREL is just pointing in the z direction. So this is actually simpler than the previous case. So this just points upwards, and this is moving. It is said that it is, where is it? Constant rate relative to this thing. So there is no ARL existing. So that is what it is. So, okay. In which case, if we were to attach the RFR, now we are able to see this shaft or this boom is actually rotating with this about this hub, and the entire system is having a rotation like that in the opposite direction like that about the vertical. So these two make up for its angular velocity. So what is this? This will be omega 1 plus omega 2, and we have written what this is. So this is from here. We can see what is omega 1. It is minus 1.5 k minus 4 j. So I'm just writing with I, j, k in order so that when we take cross products, we don't mess things up. So this is 4j minus 1.5 k. Very well. So we have found out, okay, what is asked is the magnitude of this. So what is the magnitude? It is nothing but plus minus 1.5 squared. So this comes to 4.27 radians per second. Very well. Now we should always remember that before doing this, we should always write it as symbols, only then plug in the numbers. Because if we were to differentiate this, we won't consider this as a variable, whereas in the question, it could be a variable. It is not necessary that it is always a constant. This entire thing's time derivative. So this will be omega 1. This is the vector. I'm just writing it with the minus sign attached to the unit vector rather than the magnitude so that it becomes clear. And then this is now this entire thing we have to take the time derivative. So what will this come out to be? This will be omega 1 dot minus k cap plus omega 1 into minus k cap dot plus omega 2 dot minus j cap plus omega 2 minus j cap dot. Again, we have been told for simplicity, these two velocities are constantly rotating. Everything is constant. Okay, rotates at this and this is constantly rotating. In which case we know magnitudinally there will be no change. This is 0. But if it is 0, then why are we doing it this way? Is because in case it is non-zero, we should know where that value comes in. For example, in the lecture, there is one analogy that is given, that we just take this crossed with the actual vector and then we go about calculating the accelerations. But that is specific, even it is mentioned that it is specific for the case where there is no magnitudinal change. If we were to do it from first principles, we will not miss that magnitudinal change and we will know where it actually comes. Okay, so in this question, which is the coordinate that is actually changing time is what we need to understand. So we can see that there is a tower which is rotating about the vertical, and then this boom is connected to that tower. So at the next instant, what will its location be? So at the next instant, because of this, the boom will be something like this. At the next, after that, so it will be rotating like this, and it will have rotation about its own this thing by virtue of this omega 1. So essentially, if at the next instant it will be like this, I can see that z, which is pointing like that, which is currently pointing like that, after some time it will point like that, then it will point like that. So z is actually changing its direction with time. So k cap is not constant, whereas the vertical still remains same. So this doesn't change with time. I hope that is clear. Okay, so we know this is nothing but omega 1 into minus k cap dot. Again invoking this relation which we have identified from our vector algebra. What will this be? Omega 1 into minus. In this case, what is this omega for this question? It is whatever the boom is having, because by virtue of that only z is changing direction. Because of this omega 2, the boom goes like this and then z becomes that. At some instant, it will be like this and z will become that. So it is changing by virtue of this omega 2. So that omega 2 is omega over there. So this is omega 2 vector, okay, crossed with k cap. But omega 2 vector is actually minus 4 j cap. Therefore, substituting, we get alpha boom is given by omega 1 into minus 4 j crossed with k. Why don't I replace omega 1 also with its, what is omega 1's magnitude? It is 1.5. So what is this? 1.5 into 4. So this is 6. This is 6 and then I j k. This is j cross k, which is I. So alpha comes out to be, positive. I hope that that is clear. It is 6j, 6i, sorry. Very well. So we have got alpha and we have got omega previously. So this we know it is 4.27. 27 radians per second. Then what is asked? It is per second squared. Okay, let us go ahead and attach the rotating frame of reference to this point. Now what we need to calculate is the acceleration and velocity of the concrete block, similar to our previous question. So how do we go about doing that? The velocity of the block is our velocity of the tip plus omega RFR cross R of that block with respect to tip plus VREL. Similarly, acceleration of the block is nothing but acceleration of the tip plus omega RFR plus 2 omega cross VREL plus AREL. So in this question, what all do we know? Tip, these things we can calculate. Omega RFR, we know how it is rotating about the vertical. So that we can calculate. Alpha we can calculate. We know VREL doesn't, VREL is given to be 1.2. AREL doesn't exist because it is said that it is going with a constant angular, constant speed of 1.2 meters per second relative. Okay, so in that case, I will leave it here. I will calculate these values, substitute, and then when I post this sheet, I'll upload it with the filled up answers, because I just don't want to be doing cross products throughout the class, throughout the session. What it is trying to say. A dish antenna is having angular motion in the directions as shown. Okay. So basically, because of this connection, this is having some angular velocity about the vertical, and it is also having some angular acceleration, magnitudinal change about the vertical, and then it is getting lifted like this. Sorry, it is getting lowered like that with this omega. So let us see what is being asked. At some instant, the magnitude of the angular quantities are as shown. Based on the data given, answer the following questions. Precision would be observed in this case in the dish antenna, true or false. So basically, what is precision? It is when the angular direction of the axis of the angular velocity vector itself changes. So it brings about this motion. So if we see, we have this omega 1 and omega 2. So if we were to add this up, so this is pointing like that, and then we have this pointing like this. So its actual angular velocity vector is like this. At some next instant, it will be in some other plane because of this directional change. Because of the rotation of this, it is actually changing its direction. So yes, it will be observed. because of the directional change in the direction of the axis. So then what is asked? What is the magnitude of the fan blade of the dish antenna? Okay, I think that got copied anyway. So what will this be? This will be omega 1 plus omega 2. So what is that? Omega of the antenna is omega 1 plus omega 2. So we can see what is omega 1. It is rotating in this direction, pointing towards plus y direction. Okay, so this is a correction. Actually, this will be dish antenna. Of the dish antenna, what is the magnitude of the instantaneous angular velocity? So it will be nothing but omega 1 plus omega 2. So let us go ahead and substitute that. We are able to see that this omega is pointing in the positive x direction. So omega 2 vector is nothing but plus 0.5 I. This plus 0.5 I, and omega 1 is nothing but it is plus 1.6 J. Omega of the dish antenna is nothing but 1.6 J cap, sorry, 0.5 I plus 1.6 J. So this is what it is. Now we have been asked the magnitude, so we can see what is that. 0.5 squared plus 1.6 squared root over, so it is 1.676. So magnitude of this is 1.676 radians per second. Okay, so next what is asked is what is the instantaneous angular acceleration is what is asked. Now we know omega of the dish is nothing but omega 1 plus omega 2. Omega 1 is about J is about I. So alpha of the dish is nothing but omega the dish dot, which is omega 1 dot J plus omega 1 J dot plus omega 2 dot I plus omega 2 I dot. From the question, now this happens to be a question where magnitudinal change is non-zero, as opposed to all our previous cases where magnitudinal change was zero. Here we are able to see that omega 1 is there and omega 1 dot is also specified. It shows, now we have to, one thing that we need to keep in mind is we know that it is pointing in this direction. It is pointing in the positive direction. Whereas omega 1 dot, if we see, it is pointing in the opposite direction. What does this imply? This implies that omega 1 is slowing down with time. So when we substitute for omega 1 dot, we should substitute it as minus, because these two directions are opposite. So essentially omega 1 is slowing down because of omega 1 dot. So that is the only change that we need to keep in mind here. So alpha of the dish is equal to omega 1 dot is minus 0.2 j cap, and then j cap doesn't change. I'm able to see that once this is housed, essentially even if it were to rotate, the dish is rotating like this, but at some other instant it will be like that, but the vertical still remains the same. So j cap dot is essentially 0 in this problem. So j cap dot is 0. And then omega 2, I can see this is given to be constant. There is no other magnitudinal change given. So this also happens to be 0. And then this will exist. So this will be plus omega 2 plus omega 2 into, now again let me write that, n cap dot is omega crossed with n cap. So what will this be? I cap dot will be, I cap is changing because of this omega 1. Because at this instant I cap is like that. Secondly, it will be like this. So it is changing with time. So what does that give me? It will give me omega 1 j cross I. Now it is just a matter of substitution. This will be minus 0.2 j and then I j k. So j cross I will be minus k. So this will be minus omega 1 omega 2 k. What is omega 1 and omega 2? It is 0.5 and 1.6. So let me substitute that. Minus 0.2 j, and then this will be minus 1.6 into 0.5. This is 0.8 k cap. Very well. So we have been able to find the angular acceleration vector and angular velocity vector. So recession will be observed. Yes. Then what is the magnitude? This we have found out. What is the angular acceleration vector? So 0.2 and 0.8. So we found this is 0, this is 0.2, and this is minus 0.8. So these quantities we have found out. So now that we have got omega dish and alpha dish, let us write out r of point P with respect to Q for this problem. Let me take the figure here. Let me take the full figure here. Copy. And let me put it here. Okay, so what does this come out to be? I can see that point P will be made up with vectors like that. One will be along K and one will be along Y, that is J. So its length is 3 meters. So this will be 3 into cos 35, sorry, cos 25 K cap plus sine 25 J cap. So R of P with respect to Q is nothing but 3 cos, what is this? 3 sine 25, it is 1.267 or 1.268 J, and then 3 into cos 3 sine 25 is 1.267. 3 cos 25 is 2.719. Okay. So this we know. Now once we know this, now from relative motion analysis, we know that velocity of point P velocity of point Q plus omega dish cross or P with respect to Q. Velocity of Q is 0 plus omega of the dish is, what is it? It is this quantity. So let me put that here. Delete. So this crossed with this quantity. So this is one question where we actually have to do cross products properly. So velocity of P, I can write this as, using that mnemonic ijk. So this is 0.5, 1.6 and then 0. I have just populated these two here. It is crossed with 1.268 and 2.719. So as we saw in the very first session, how to do cross products between two three-dimensional vectors, that is what we are employing here. So even then, I suppose I had mentioned that it will come in handy when we are actually dealing with three-dimensional motion, three-dimensional kinematics. So what will this come out to be? I know for I need to consider these four and then do it systematically. The cross multiplication. So it is 1.6 into 2.719 minus 0, and then it will be plus j into these four quantities will come, where this I'm taking first, that is why I'm putting plus outside. So this will be 0 minus 0.5 into 2.719. Mind you, these are not cross products. This is just simple multiplication. For the paucity of symbols, I'm just using that. Plus k cap into 0.268, sorry, 1.268 minus 0. So velocity of P, let me calculate this, 1.6 into 2.719. This comes out to be 4.355 I. And this will be 0.2.719. So this is 1.356 J, 1.268. So this is 0. Plus 0.63 K cap. 63 K cap, sorry. Plus 0.63 K cap. Very well. So this we have found out the velocity of point P, the absolute velocity of point P due to this motion. Similarly, we have been asked to report the so its magnitude, we just need to populate its magnitude. So this will come out to be 4.35 squared. This comes out as 4.59. meters per second, not second squared. Next, we have been asked to find the angular acceleration of this point P. So the angular acceleration, similar to this angular acceleration of point P also we can find out. Similar to this, the total acceleration of point P also we can find out, which will be nothing but acceleration of Q plus omega cross r P with respect to Q plus alpha cross r of P with respect to Q will be 0 plus what is omega? Omega is this quantity, omega of the dish, omega cross it is rp with respect to q, it is this quantity plus alpha. Alpha we have found out it is this here, alpha of the dish. Crossed with again this vector. So let me go ahead and do this. So acceleration of p will be, first I need I, j, k. Now we have already calculated this quantity, this omega cross r. This is 0. This is 0. This quantity we have already calculated. We just calculated it as this. And then I just need to cross it with one more omega. So I'll just write it like that. And then omega is 0.5 I, 1.6 and then 0. And then crossed with, so it will be this vector. So 4.35 minus 1.36, 0.63. So 4.35 minus 1.36, 0.63. So this takes care of the centripetal acceleration component. Then I need to account for the tangential acceleration component, which is the cross product of these two vectors. So let us go ahead and write that. So it will be nothing but I, j, k crossed with 0, minus 0.2, minus 0.8, and then this is 0, 1.268, 2.719. So I just need to open this out and do the cross multiplication. So let us do that for one problem. So it will be I cap into 1.6 into 0.63 minus 0 plus j cap into 0 minus 0.5 into 0.63. What I have done is I have taken j and I have multiplied this first. That is why I am taking a plus here. General mnemonic when we find determinant is we take minus and then multiply these first. So it is one in the same. So I am just doing it in the reverse order. Plus k cap into minus 1.36 into 0.5 minus, let me write it here so that there is no confusion. Plus k cap into these these four quantities I need to take. So it will be minus 1.36 into 0.5 minus 1.6 into 4.35. So this is just accounting for the first cross product. Then I need to add one more vector from here. So here I'm able to see that I cap, see j and k will be 0 because this has 0. So when we consider j, it will be 0 into 0 minus 0. Similarly for k cap 0 minus 0, fortunately. So for I, it will be just the cross multiplication of these two quantities. So it will be minus 0.2 into 2.719, 2.719 plus 0.8 into 0.8 into 1.268. So this comes out to be what? So it will be 1.6 into 0.63. This is 1.008 I minus 0.63 into 0.5. 0.315 J 36 into 0.5 minus 1.6 into 4.35. So this is minus 7.64 K cap. And then this is minus 0.2 into 2.719 plus 0.8 into 1.268. So 0, this is nothing but plus 0.47 I. So if I were to add these up, ultimately what do I get? 1.008 plus 0.47. It is 1.478 I minus 0.31 minus 0.315 J minus 7.64 K cap. So this is the acceleration of this point P. Now we saw that it becomes a little messy when we do cross products of three-dimensional vectors, but nonetheless it is required for our analysis. So 1.478, so this is 1.478, then we have minus 0.315 minus 7 point minus 7.64. Okay, so I hope this is clear. So essentially what we have been seeing in this session is that once we have three-dimensional vectors, cross products become a little involved, but our basic principles of relative motion, like applying RFR equations, the rotating frames of reference, VREL, AREL, and then 2 omega cross VREL, the correction for Coriolis component, all these essentially remain same. What changes is that our vectors are now in three dimensions. Basically, initially we were considering cases where our alpha and omega were both parallel in the vector form. Only the magnitudinal change was different. Maybe alpha was negative or positive. It was always along the same direction, but we have relaxed that constraint in order to study a different class of problems in this session, which essentially deals with the change in direction of the axis of the angular velocity vector. For example, if we have the angular velocity vector like this and it is spinning, it might also rotate like this. By virtue of that rotation, which is called precession, there will be additional quantities that we need to account for, which is what we have detailed. We have in which is what we have threadbare seen in a few examples. The While attaching the rotating frame of reference, there might be cases where we need to account for acceleration, AREL, and velocity, VREL. Some might come from circular motion, some might come directly from the quantities given in the question. So the idea is, once it is given, how to identify these pieces of the puzzle and then put them together in our equations, which we have done umpteen number of times. The only difference is that these quantities, these vectors which we had put till now, were not always having three-dimensional components. Now it is having three components. So that happens to be the only difference. Other than that, uh, there is essentially no difference between in terms of complexity. Three-dimensional kinematics is not very much different from two-dimensional kinematics, given that all our equations of analysis remain the same. So with this, we conclude the week 12 for this course, which happens to be the last week. So next week we will be having one session where we can maybe have a comprehensive doubt clearing where all the doubts, that is, we can have representative problems from each week. That starts with basic forces, then comes to equilibrium, then beams, trusses, beams in that order, and then we have virtual work, and then some principles of friction, some energy principles also we will discuss, followed by belt friction. Then we step into dynamics from basic particle analysis. Then we bring in the rigid body motion, where we study absolute motion first, then we study relative motion. Relative motion we study with two, three concepts, basically either coincident points, then we have rotating frames of reference, then we have non-rotating translating axis in the opposite order. Then we step into more detailed analysis of rotating frames of reference and how to analyze constraint systems, followed by our basic discussions on 2D kinetics, where we saw whatever kinematical quantities that we had found out, how to relate them to forces and torques. So that is what we saw in the last session, which was week 11, which had to do with 2D kinetics. And now we have stepped into 3D kinematics, which concludes this course. So I hope that these live sessions were of some assistance to whoever has been following this. So I hope it has served the purpose well. And if there are any questions, you please feel free to raise them in the forum. All those means at your disposal. You please use them to reach out to us should you have any questions. So with this, we can formally conclude all the live sessions. Next week, we will just have one maybe a doubt clearing session where we will have representative problems from each week, which we'll take before the final exam. So those who are taking the exam, I wish them all the best. I hope these sessions were of some substance and value to you. So with that, I'll conclude this live session. So thank you for watching.